Finally, we will discuss how the split cable forces affect our anchor and foundation analyses. We can lump these items together as our abutment analysis. But before we dive into that, I'm going to stop for a moment and ask, would increasing mu, the coefficient of friction, make this check more conservative, or would decreasing mu make this check more conservative? The correct answer is that decreasing mu would make this check more conservative. This is because it allocates a larger portion of the cable force into the anchor if we're decreasing our friction across the tower column saddles and walkway hump. Now, when we go in to integrate our split cable analysis into the foundation analysis, we want to remember that this primarily affects our overturning and our bearing calculations. And instead of having to recalculate all of these forces, we can just draw these directly from the tower analysis tab. And the horizontal and vertical cable forces at the tower will just be the sum of the vertical forces at the two tower columns and the walkway hump. I have here, 2 PV hand plus PV walk would be our total vertical forces, and 2 PH hand plus PH walk would be our total horizontal forces that contribute to our overturning moment and restorative moment at the tower and foundation point, 0, 0 that I've labeled here. And finally, the last structural subsystem affected by our cable split will be anchor analysis. Remember from our previous example that splitting cable forces has a significant impact on the anchor forces. So we can calculate the vertical and horizontal forces at the anchor as the sum of our previous forces. The vertical backstay and horizontal backstay forces split into both the handrail and walkway contributions, which I've labeled here. And the second component of the anchor analysis is our PH tower term. This term can be a bit confusing, so it's helpful to explain with a free body diagram. To start, force flows from the walkway and into the cables. And as the cables pass over the tower columns and walkway hump, the subforce dissipates into these via friction. These are labeled as the gold and magenta arrows here. But by the time we arrive at the anchor, we have the force in green, which I described equations for above. If we are solely analyzing the anchor, which we'll do later in later lectures, this green force is sufficient as the sum of our backstay, handrail, and walkway forces. However, the anchor analysis description can be a bit of a misnomer, because we are doing both. We're analyzing the anchor component as a reinforced concrete beam, but we're also looking at the entire abutment in sliding and uplift. Therefore, we need to include the PH tower term, because when we are looking at the entire abutment as a block in sliding, it is a summation of our green, magenta, and purple forces here. So, how do we calculate our PH tower term? This is essentially the contribution of friction over the tower. So it will be the horizontal mainspan tension minus the horizontal backstay tensions. You can see our mainspan tension here and our backstay tensions here. And finally, the PH tower term adds back into our horizontal anchor forces when we are evaluating the entire abutment sliding as a block. So our total horizontal driving force, RS, is going to be that PH tower term plus our PH hand back plus our PH walk back, which, as you remember, come from this summation here that we talked about in the beginning, just a summation of our backstay forces. In the basic course, this was just our handrail backstay force multiplied by all of the cables, and in here we're breaking it up between handrail and walkway, and our force would be lower. Our total force will be lower. Now that concludes our discussion of cable splitting and how to incorporate it into your design analysis calculations. Remember that it will notably affect our cable analysis, foundation analysis, tower and anchor analysis. In the next lecture, we will discuss which friction coefficients to use when calculating these forces.